Okay, so in the last unit, we examined electric charge and electric fields. And we looked at how charge is created by the buildup of electrons. And when we have a area of space that's charged, that generates an electric field around it, which affects the other objects, other charged, or it even attracts uncharged objects. So in this unit, we're going to study what happens when we take that electrical charge or take those electrons and harness them into an electrical circuit. So we use wires to contain the electrons and guiding them from place to place. So we'll start by looking a little bit about charge and current in general and that relationship, and then go on to examine electrical power and the costs behind electrical power. So what we pay, what it costs to run a light bulb or a refrigerator, for example. And then in the end, we'll take all this information and apply it to electrical currents and look at building a few of these electrical currents. So we'll start by looking at what we did in the last part of this chapter, which is potential difference or voltage. Okay, so a potential difference is required for a current to flow. Okay, and charge flows from a higher potential to a lower potential. So if you remember, previously in the unit, we talked about a battery, and we talked about how a battery has a negative side of a battery and a positive side of a battery. Okay, at the negative side, we have a buildup of electrons in that area. This creates what we call a potential difference. So here we have what we call a high potential at the negative side, and we have a low potential at the positive side. If we could connect those two sides with a wire, the electrons would start to flow from the high potential to the low potential. This is actually similar. We're going to look at each of these ideas and apply the idea of water, because the water flows just like an electrical current does. So with water, the same idea, the potential energy from the top, so the height of the well here, or the water storage tank, right, to the bottom is the voltage. So how much energy do we have? The higher we lift this up, the more the voltage becomes, because the more energy it has to drop down. Okay, so that is how we can examine voltage through water. Current is the flow of electrons through a conductor as a result of a potential difference. So if we have a voltage and we attach a wire, the electrons will start to flow. Current is how much charge moves from one place to another in a given amount of time. Okay, so current is defined as the rate of flow of charge, or Q we had before. Q is the charge, T is our time in seconds, Q we always want in coulombs, and a coulomb per second, or charge per second, we define as an amp, or amperage. Okay, where 1 amp is equal to 1 coulomb per second of charge. Now, just like voltage, we can imagine this as in terms of water. So both of these tanks being at the same height, okay, from here to here, they both have the same voltage, which represents the potential. But you'll notice that the tank on the left has a wider spout for the water to come down, whereas the tank on the right has a very narrow spout. Okay, so the wider one allows more water to flow in the same amount of time as the closer one, which means it has a higher amperage in the tank on the left-hand side. Now, something to note about when we talk about current. So in physics, up to this point, we were talking about the current as in the flow of electrons from one point to another. In physics, we often talk about conventional current, which refers to the flow of positive charge, not electrons. So it's actually the reverse of the flow of the electrons. So if you imagine the electrons in these water examples going from the top to the bottom, conventional current is the current that goes from the bottom to the top. The reason we use conventional current is because current was developed, the idea of current, before the discovery of the electron, which, they said it has to flow one way to another. Let's make it flow from positive to negative. We later on learned about the electron flowing from negative to positive, but all the physics equations and everything were already established at that point. So it stayed as conventional current, which is what we now call it and what we use. Let's take a look at an example of how to calculate the current in a system. So a service station charges a battery using a current of 5.5 amps for 6 hours. How much charge passes through the battery? Okay, so what do we know about this? We have that our current, or I, is 5.5 amps. We know our time is 6 hours. Now when we calculate this, we always want time in seconds. So when we convert, multiply by 3600, we get 21,600 seconds. And we're looking for our charge. So we use our new formula that we just examined. Our current is equal to charge over time. So how much charge passes a given place in a certain amount of time. Charge is 5.5 amps or coulombs per second. We have our Q, and time is 21,600 seconds. Rearranging, so multiplying both sides by our time, we'll find that Q is equal to a charge of 1.2 times 10 to the 5 coulombs. You'll notice that this is a much larger charge than anything we've previously been working with. A lot of our charge before, like the charge on the balloon you found in that lab we did, was on the order of 10 to the negative 4 to 10 to the negative 6 coulombs. This is why when dealing with circuits and wires and high voltages, it can actually be very, very dangerous because we're dealing with incredibly high amounts of charge and incredibly high currents. So the last thing to talk about is resistance. These are the three big themes for this whole chapter: is current, voltage, and resistance. So resistance in a wire, the more resistance reduces the flow of current, and it's measured in ohms, which is given the Greek symbol omega. Charges lose potential when traveling through a resistance. So for an example here, if we have a light bulb, okay, how our old-fashioned incandescent light bulbs work? Just draw one up here for you to see. Okay, so we have a wire that's very, very, very skinny. So it's a high resistance wire. As the current flows through the wire, some of the potential or some of the charge is actually lost. Or some of the potential is lost. It's converted from electrical energy into light and heat energy as it travels through that wire. Okay, so resistance actually can allow us to harness electrical power as something travels through a circuit. But it will lose that voltage. So if you hook up too many light bulbs, you won't be able to have enough voltage to power them all. We'll look at that later in the unit when we get to circuits. So resistance depends on a few different things. The type of material that you're using. Some material allows current to flow easier than others. The thickness of the material. Of course, a thick wire will allow more current than a small wire. The length. So the longer the wire is, the more resistance, because the more it has to travel through. And the temperature. Okay, so like the other facets we looked at, like current and resistance, or current and voltage, we can imagine resistance as the flow of water. So an unrestricted path would have less resistance, whereas if we squeeze that path in, like in the bottom example, we increase the resistance, which affects the amount of water that can go through on the other side. So this will actually decrease the current. Now, if we leave the height the same, then the voltage would stay the same, but it will decrease one or the other. That relationship between resistance, current, and voltage is known as Ohm's law. So Ohm's law was discovered experimentally by George Ohm. And in materials that follow Ohm's law, not all materials do, but in ones that do, we know that the current is directly proportional to the voltage. So if we increase the voltage of a system, if we keep resistance the same, we increase voltage, we will also increase current, or vice versa. If we increase current, the voltage of a system will increase if resistance remains constant. Okay, most metals, but not all of them, do obey Ohm's law, and a resistor or another object that obeys Ohm's law, we call it ohmic. So an ohmic resistor is one that won't change if the voltage and current changes, its resistance stays constant. So the equation for Ohm's law, there's a couple of different ways to write it, but we can look at a relationship of current in terms of voltage and resistance. So in this equation, if you increase the voltage, right, that would cause the current to increase. So if we have an increase in voltage, we have an increase in current as well. If we have an increase in resistance, that leads to a decrease in the current because it's harder for those electrons to move through the system, which is why the resistance is on the bottom in this equation. Now, ohms are more commonly, you'll see it written as V equals IR, but this is the way in I equals V over R, how just an easy way to examine the variables. Resistance, or that ohm that we talked about, is defined as 1 volt per amp. So the symbol omega represents 1 volt per ampere. And Ohm's law refers to the fact that the resistance for most conductors does not depend on the potential difference across the conductor. Okay. What that means is that if we change the voltage, if we increase or decrease the voltage across the resistor, the resistance does not change. Again, some materials this doesn't apply to, in which case we wouldn't be able to apply Ohm's law, but everything we'll come across in this chapter will use Ohm's law and its applications and assume that it applies to the materials. So let's take a look at one more example. So a 12-volt battery is connected to a device and 24 milliamps of current flows through it. If the device obeys Ohm's law, meaning the resistance doesn't change when we change the current, how much current will flow when a 24-volt battery is used? So let's start by labeling all of our variables. So we have our first voltage that we're given is 12 volts, so we'll call that V1, and we have I1 is 24 milliamps, which is equal to 0.024 amps. Okay, we also have our V2, which is 24 volts, and our goal here is to figure out I2. Now we know that between the voltage 1 and the voltage 2, the resistance remains constant. So if we can find the resistance using the initial conditions, we can apply that resistance to the second conditions to figure out the current. So we start I1 is equal to V1 over R. Okay, I we have 0.024 amps. It's equal to 12 volts. You want to make sure you're in those standard units when working with these values. And we get a resistance of 500, approximately 500 ohms. Okay, we then can apply that, so we assume that this value remains constant. When we change the voltage. So we then apply that over here. So I2 is equal to V2 over R. I2 is 24 divided by 500. And we get our second current when we double the voltage. our current, we see also doubles. Okay, which makes sense based on our equation. So twice doubling the voltage will double the current, or half the voltage would half the current. Okay, and lastly, for this piece, a practice problem. So a 1.5 volt battery is connected to a bulb whose resistance is 10 ohms. How many electrons leave the battery each minute? So with a practice problem, now's a good point to pause the video for a second, take a minute and try this problem out, and then come back to the video to see if you got the right answer. Okay, so starting with writing our variables, we know our voltage, 1.5 volts. Our resistance is 10 ohms. Our time is 60 seconds because we're trying to figure out how many electrons leave each minute. And in order to find the number of electrons, we're going to have to first find our charge. How do we find charge? Well, we can use the current because we know current is charge over time. So first we have to find current though. So starting with Ohm's law, I equals V over R. We get 1.5 over 10, or a current of 0.15 amps. We then use that value. So we know that current is equal to charge over time. It's 0.15 Q over 60. Or that the charge of our system is 9.0 coulombs. Okay, so that's the charge, but that doesn't tell us the number of electrons. But we do know that one electron has a charge of 1.6 times 10 to the negative 19. So if we want to find our number of electrons, we can take our charge, 9.0 coulombs, divide it by the charge on a single electron, 1.6 times 10 to the negative 19 coulombs per electron, and that gives us 5.6 times 10 to the 19 electrons. Okay, and that brings us to the end of the introduction on Ohm's law and current and resistance and voltage. So for homework, try the problem set 3.2.1. This will be posted up on the class webpage. There's quite a few questions, but take your time. They're not too hard. They just use the material we learned today in this video. Let me know if you have any questions, and I'll see you next time to talk about electrical power.